Books. So there are going to be kind of two parts of this course. Okay. So long ago, around 15-20 years back, there used to be actually two courses. There used to be a data communication course and there used to be a computer networks course. The data communication, the basics of communication is kind of the background to networks. Both used to be core courses, but when the curriculum revision at that time, the number of courses had to be reduced and something had to go. And we felt that it's okay to teach networks with a little bit of communication squeezed in, only the very relevant parts, but we may not need to teach all the details of communications. Okay. It's always good to learn everything, but then you have to prioritize and see what is more important for CS students. So right now we have one course, but we'll still have something at the beginning, which is more data communication, and we'll see what it means. You will see the things that it means. And then comes the actual higher layer networking like TCP, IP, Ethernet, the things that we are generally talking about. So when I talk about these two books, the first one is primarily for the first part. Second one is primarily for the second part. And I will point out when we teach, where am I teaching from, so that you can easily follow. And these references, the first one is basically this Farrouzan book. So this Stallings book and Farrouzan book are kind of interchangeable. So the other section is, for example, he is making slides out of Farrouzan. And we have looked at both books thoroughly. You will find the same topics that we cover, just a little bit detailed difference and so on. But all the relevant things are there. So you can actually follow either Stallings or Farrouzan. I have no problem. Okay. Farrouzan's TCP/IP book is also good, but this Komar is kind of a classic, so I prefer that. And this TCP/IP guide by Charles Koziak, it's an old book, but it's kind of the definitive guide to everything TCP/IP. Don't get kind of scared by the size of these books. Okay, the TCP/IP guide is a huge. I have the hard copy of that, so it's a huge, thick book basically with everything that you need to know about TCP/IP and its a suite of protocols. But again, we are, the guidelines will be what we cover in class, and then if you need a little bit more detail and so on, it's a nice book to look at basically. So we'll start. If you have questions and all, confused or something, then just keep on asking me as we go on. Okay. There are many other books, but this I find is kind of easy for you to follow. Course website will be this, where I put up slides and everything. It is there now with hardly anything, so I will keep on updating it as we go on. Okay. What is a network? Okay. So you all know what is a network. It's a collection of machines there, so it's kind of an introductory slide that communicate with each other over some communication medium. Okay. And what is important, two machines may be directly connected by a link. You can directly connect them by a wire, or for example, two things directly communicating over wireless, or you can communicate through other machines. Okay. And when you communicate through other machines, basically you get something like, so if these are your machines, just give me a second. And they communicate with other links and so on. So basically you see what you get is a graph. And we will see some of the graph algorithms at play at some point of time. Now, what is one thing that is interesting to know? That not all machines or devices, okay, slowly I will start using the term devices, that you will see in a network are generators or consumers of data. Some of them will be source. You send an email from your machine is the source, your friend gets it, your friend's machine is the destination. But then there's a lot of intermediate nodes in the middle, which just facilitate in the transfer. The packet passes through them, your mail passes through them, but they do not per se generate any data. And a classic example is a switch or a router. You all know about these things mostly, okay? At least heard about it and so on. Okay. And then what is a protocol? So these two things, this term is extremely important in network. Okay. So in general, a protocol is a rule for communication. So when, For example, we are taking this class. There are certain protocols. What is the protocol? When I speak, you don't speak. Okay, so that is timing. Okay, or if I speak and you say, sir, I have a question, I detect that you are also speaking, I stop. Okay, so that's timing about who speaks when. Okay, that is the timing. Second thing is like, I speak in English. We have kind of a priori agreed that we'll speak in English. If I speak in German and you understand English, is not going to work. Okay, so it's basically very common to what we do every day. Only thing in network, we'll see it's more formally defined. We must speak the same language to understand each other. So it specifies the syntax, semantics, and timing. When I send a message, okay, what is the syntax of that message? When you send a mail, okay, will your sender's name will be before the destination name, or the destination's name will be before the sender's name? That's the syntax, because the router has to understand that. Router has to know the first one is the destination. Therefore, I should pick up the destination and see how to send it. So that agreement has to be clear. Then the semantics, okay? How do you specify? Okay, what does it mean here? Okay. And then the timing of the communication. So we'll see this thing. This kind of very generic slide because everybody has it. What is a protocol? But we'll see. It's not very important to remember or mug anything else. What is a protocol or so. Bit of history. Network has a very interesting, very interesting history, which is both, you need to look into it a little bit, just both out of fun and for another serious reason that I will point out. Just let me just go through the few slides. So network started with telephone networks, and it established a direct communication between distant indirectly connected systems. Basically, so old telephone networks, you have not seen them. You are very old, so we have seen them. So before you make a call in the old manual exchanges or even digital exchanges, telephone exchanges, what used to happen is, even if you are making a call to US, actually a path used to get set up all the way through the exchanges on the path to that subscriber's line, your destination person's line. Physically, a path used to get set up either for manual exchange or for digital exchange, the digital path. So there is a connection. And then everything that you speak will go through that same path. So this is what is called a circuit switch. We'll look at it in more detail later on. No need to remember too much. Okay. But basically, kind of a circuit, a continuous circuit gets established from the sender's handset to the receiver's handset, and then you speak. These were the old landline phones. So phones were much before this. The first telephone switch was, to the best of our knowledge, is 1878 in US. Just a bit of history. This is from Wikipedia. You should read this. It's again like you have grown up in an era where technology is omnipresent. We have kind of seen technology develop, and our parents have seen it even. We kind of laugh at the things that they used to have. You laugh at the things that we used to have. Okay? But this paragraph is kind of summarizes like the thrill of doing something for the first time. This was the beginning of packet switching. What is a packet switching? So packet switching says, rather than trying to establish that entire connection in one go and then sending everything over that one go, I'll try to break up your message into small packets. There's again a design parameters there. How big? But we're not going to answer that now. We'll see the protocols in play later on. Okay. And then I'm going to route those packets. So each of those packets may actually go through a different line. It's not necessary that all of them needs to go to exactly the same path to the destination. So that's the essence of packet switching. Okay. So this first internet kind of was sponsored by DARPA, which is the US government's Department of Defense's research agency. Okay. And it was called ARPANET. So you can read this. So this first ARPANET link, the first communication was made between UCLA and Stanford. And this red thing is what I want you to read. Leonard Kleinrock is again a very well-known personality in this area. So I said, we typed the L, we asked on the phone. So how do you know whether your L has gone on the other side or not? Okay. So you're on the phone, which is already established, and you have the computers where you're typing L and asking the other party, do you receive the L? So there's, do you see the L? Yes, we see the L, came the response. We typed the O, we asked, do you see the O? Yes, we see the O. Then we typed the G and the system crashed. And this last line is what thrills me a lot. Yet a revolution had begun. You have been able to send 2 characters. Seems laughable. Okay, but you have to kind of put yourself back. That's how technology starts. And you also have challenges. Okay. Now, even with all these technologies and so on, we are doing something very small is also still kind of fundamental. Okay. So it started with a 4-node network. Okay, between UCLA, Stanford, University of Utah, and UC Santa Barbara. And then it just kept on going. Rest is history. This was ARPANET, this 4-node network in 69. This is 70. This is 72. This is 77. Okay. Then in 1981, NSF thought that it will connect all the academic institutions, the CS departments. So they call it CSNet. Well, not the academic institutions but only. The CS departments took the lead basically. And then the next, so that was still ARPANET. And the next big thing was National Science Foundation in US funded 5 supercomputing centers in mid-80s. They are still there. And to connect them, because the supercomputer used to be extremely costly, extremely costly. They wanted these 5 people to kind of use each other's resources rather than putting all the things in one place. So wanted to connect them in network. So in 86 called NSFNet, and ARPANET was decommissioned in 1990. And this is the other interesting things. This is the backbone speed. Okay, so backbone speed means basically think of a link connecting 2 of those supercomputer centers. Okay, it's like a 56 kilobits per second. It's almost minuscule. When it went to 1.55 Mbps, it was called a T1 line. Okay, it's there in commercial for a long time earlier. It was like huge at 1 point, but look at the jump. 56 to 1.55, then within 3 years, 45 Mbps, which was the T3 line. Okay. And the rest is history. I will cut short the history. You should read it. So then this, in the 90s, what happened? Commercial operators started coming in. Sprint, AT&T, so not Sprint in those days, AT&T and others. Okay, Merit, AT&T, those companies. And then kind of there was talk. So NSF kind of outsourced the operation of these things to Merit. Then other companies started coming in, and then by late 90s, basically it was completely almost taken over by the commercial operators. And NSF kind of took a kind of little bit regulatory role in the meantime, and then kind of handed it over to different agencies out there. Okay. So one is you should read it sometime. Okay, from different places, history of internet, just type and you will find very interesting things. It's for fun. The other thing that you will see when you study this course, okay, and this is the third thing of the design-oriented systems and so on, the third thing that you should remember and try to kind of assimilate. It's going to be very confusing in some way. Okay, it's going to be confusing because first of all, you will see a huge amount of terminology. Okay. I already threw in some. I threw in a T1 line, a T3 line, and so on. Okay. And then some of those terminologies and things that you study are kind of old. If you look at an actual device today, you will probably not find it there, or find it only in very niche areas. Okay. So then the natural question confusion is, why should I study them? Because see, this is a technology-oriented course. So the problem is that as technology advances, there are things that become obsolete and newer things come. So the question is, do we need to study those obsolete things? That's the first question. So there will be a lot of terminologies, a lot of things. Okay. In my opinion, not all, but it's very important to study some of them. Okay. Why? Because again, from the design thing. They were beautiful things in their times, and you should understand why did those designs happen, in the context in which they happened, how did they make the choices, what were the trade-offs, and so on. So you understand the design process, and the other thing that happens is that you take some of their ideas forward. You may not be using that as a whole, okay, but you take some of their ideas forward. Okay. The classic example you will see is CSMA-CD. Many of you have heard of them. Okay. So CSMA-CD in modern day Ethernets, switched Ethernet is almost not there, high-speed Ethernet. But then CSMA-CA is still there in wireless Ethernets. And the CA idea came because CD was important, kind of impossible to do in wireless. So you need to look at some of those important things as it happened, the technologies, because they were used till some time back, and they are great designs. You understand the process of designing at your age, okay, and you take sometimes ideas from there. So token ring network, another thing. Again, I'm throwing in terminologies. So token ring network as a local area network, LAN, is not there. But then the concept that the token ring network had of token passing, you will be using in many different areas. Okay. So it's going to be, let me warn you and ask questions. Okay, I will try to clear up as much as I can. Okay, it's going to be confusing. There's a lot of terminologies. Sometimes you will see things that I will teach and then I will say, no, but it's not used anymore. But I teach it for that reason. And in my support, you will see almost any textbook that you see will have something on it. So that's the other question, that if it says, no, if everybody thought it's unimportant and SIR thought it's important, why would the textbook start and talk about it? And in consequence, if you go out and talk to people, you go to interviews and other things, vivas, you give gate or whatever, basically, people will still ask you questions on it. So they're important to know. Okay, from every angle, that I said, from the learning point of view of design, okay, taking ideas from them and so on, to the point of in the real world, people will be asking you those things, you know, in your interviews and this and so on. Okay. But I warn you, that's the other thing. You know, I don't use the word warn in the bad sense. That be on the lookout. There will be lots of terminologies. You will see some terminologies, the definition has changed. You know, what we used to call some, you know, that same thing earlier, we call it something else now. Okay. So try to make sense out of them. I will help you. That's one of my goals. Try to make sense out of them as you go on. Okay. Little bit of history of LANs. Developed in something called Xerox PARC. Anybody heard of Xerox PARC? Yes, no?
Yes, sir.
Okay. What is Xerox PARC?
So it stands for Palo Alto Research Center.
Right.
It's where a lot of innovations took place. Like Xerox had a team of brilliant scientists of that era,
Right.
and did a lot of research.
Exactly. Very good. Very good. Yeah, and it's funny. This other thing. Technology is a beautiful thing. And you should, you know, kind of read the history to see, you know, both the technological side and the commercial side of things. Okay, I'll explain. So Ethernet started in Xerox PARC in the early 1970s. This is very famous paper. It's publicly available. You should go read just for the fun of it. Okay, which kind of explains the design of the basic Ethernet. And then in 1980, DEC, Intel, and Xerox. So DEC used to be the big company in those days. Okay, so two of the biggest, you know, mainframe computer manufacturers were DEC and IBM. IBM has stayed on. There were many others. Okay, there are many others which have died. DEC, Digital Equipment Corporation, Electric Equipment Corporation. Everybody calls it DEC. So DEC died in the early 2000s, basically. But it was one of the biggest things. And there are funny histories about DEC. I'll talk a little bit. The first class, so let's chat a bit. Then it was revised at Ethernet 2. Then IEEE took it over. This 802.3, there's a series of standards actually. We'll talk a little bit about it later on. So they are the de facto standard for LANs. And again, from a technology point of view, the original LAN, the original one that was developed by Xerox PARC was even slower. It was, I think, 2 Mbps or 3 Mbps something. But in the first commercial working LAN that was sold was 10 Mbps LAN. And we now talk about like 100 plus Gbps LANs. Okay. So 10 Gbps LAN is very common. 1 Gbps LAN is everywhere. All your new laptop, everything comes with 1 Gbps LAN. 10 Gbps LAN is quite common. 140 Gbps, 100 Gbps is there for quite some time, but costs money. And there's work going on in more higher than 100 Gbps also. So Xerox PARC used to be very interesting. So Xerox PARC, Xerox, the name Xerox that came from it, photocopying. A huge company in photocopying business basically. So they had so much money, they just, people used to establish this research lab just for people to do things. There's so much money from the other business. And 3 of the biggest inventions that you can think of today that you use every day, okay, came from Xerox PARC, among other things. The first PC, the original version of PC was built in Xerox PARC. The first graphical user interface, the notion of graphical user interface in nascent form was developed in Xerox PARC. And Ethernet was developed in Xerox PARC. And the funny thing is Xerox made money out of none of these things because they did not think of it is important to commercialize them. Nobody thought a PC is going to, because it's, it's early 1970, I think it was 71 or 72 or something, I forgot exactly. And the world is full of big computers. You have not seen there is a literally room full of computers. Okay, I've worked on them. And as students, your only access to the computers were 2 small holes in a wall. In one of them, you will give your input punch cards, and the other one, some printouts will come with your output, maybe in next day or something. You are not allowed to see those computers also. They're so expensive, has to be maintained so well and so on. Normal people like us, small people like students are not allowed to see them. We see them from far off. Okay, so nobody thought, a small machine PC like that will have any future or something. So it's all about vision. Let me tell you a story. So DEC was in the mainframe business, mainframe and what are called mini computers in those days. Okay, so these are again so many terminologies. Okay, this all disappeared. Nobody talks about a mainframe, mini computer, so on. Okay, but those were the terminology in those days. And then there was a guy called David Cutler. So David Cutler wanted to build a operating system for the PC because IBM just introduced that PC. IBM PCs were just coming to the market. So this was late 80s, mid to late 80s. And DEC thought that there is absolutely no business, no future in developing, okay, not just an operating system, a server operating system. Okay. Because IBM already had this basic OS2, which was just a text-based, simple operating system, single-user operating system. Only one person can use it at one time, and very trivial, simple things. So David Cutler wanted to develop a server operating system for the PC, and because the power of the PC was so low, they said that there is absolutely no business in it, no future. Nobody will ever want to use a server operating system on a PC-like machine. So this is funny. Microsoft in those days, remember Microsoft had no money in those days. Microsoft has started in early 80s, late 70s, early 80s. Okay, Microsoft made money when their Windows things started coming up in the 90s, Windows 3.1, Office 95, and so on and so forth. So they were doing that IBM's business. There's some money, but nothing much. So Microsoft started developing a server or put a team together, asked David Cutler to come over. David Cutler came with some of his people and Microsoft put some of his own people. Okay. They found a small team to develop a server operating system for the PC. And you have to see, Microsoft, people say copied many things and so on, etc., etc. That may be true, but you have to see the vision. Okay. And the rest is history. They did not make any money out of it for the next 10 years. But this was the genesis of the Windows NT. And now what you think of the Windows 2000 server and now Windows Server systems, 2012 and so on. Because nobody expected the notion of a single box, what was called a PC in those days, to expand into have so much power that a server operating system will actually run on it and people will actually want to run applications. So history is full of twists like this, and if you just do it for fun outside it for normal hours and so on, just for fun, not for any gain or anything, it's actually very, very interesting history. So David Cutler was considered, why I mentioned David Cutler is one of the top 5 OS programmers in the world. That was the community's view of it basically. All the big DEC OSs, which were extremely famous OSs, okay, VAX, etc., were actually developed by David Cutler. Anyway, I digress. Okay, so there is a bit of history behind all these things. Let's come back to the course. What will we do in this course? So networks can be taught in 2 ways. Okay. One is that you can start with the applications. You can start with, for example, a mail, telnet, whatever, things that you use every day. And you say that, okay, to send the mail, what do I need? I need to communicate between your machine to my machine, far off. Okay, so to make that happen, what do I need? Okay. Then comes the top layer that SMTPs and all, which an application layer uses. So you will see, we'll talk about it later on, that networking stack, the software that makes all these things work, the software and hardware, is kind of arranged in layers, in a hierarchical manner. So you can traverse that layer. At the topmost layers is the applications, SMTP, Telnet, FTP, HTTP, all those things. So you can either start from the top and study layer by layer, saying that, okay, to do this, I need this, let me see what the service in the lower layer is providing. We'll do layering and all in more detail. The other approach that we take, okay, is we start from the bottom and we say, what do I need to make this very basic communication work? Suppose I don't have this world of internet. I just have 2 machines and 1 link. What are the issues? What are the challenges? What are the techniques? Then I say, oh, I know now how to make these 2 machines work. Now what about I expand this? So kind of go step by step from the bottom and traverse the layer. The same layers you traverse from bottom onwards, basically. There are pros and cons of both approaches. And you will see in the lab, actually, because we have to start developing applications and so on, we'll kind of take a top-down approach. But we'll teach from a bottom-up. Don't worry about it. We'll kind of give you enough background to do your lab spec. Okay. So people have taken both approaches, both works. There are pros and cons of both. We prefer the bottom-up approach. So here is what we will do. We'll do basics of communication. This is the thing that we'll do very sketchy. Okay, we'll just kind of very brief overview of analog and digital transmission. We expect you to know already some of these things from a signals course. But some things that everybody kind of expects you to know. You will probably not have to deal with it directly in, developing them and something, but it helps a little bit sometimes. Okay, but we'll kind of, these are things you should be aware of because these are kind of good things to know. People ask you all the time and so on. And then transmission medium. As I said, networks, you can have wireless medium, but you have wired medium. So a little bit of that also. And this is important in the sense that if I ask you to design a network, for example, the IIT's network, which is something that I will talk about later, deep, way later in the course. So I ask you to kind of, I give you a set of hostels and so on, to connect them, build a network, new campus coming up, build a network for it. Then you have to choose devices. You have to choose what medium to use to connect them. So you need to know some of the characteristics of this medium, which one would be good for what, and so on. Okay. So it's not that you will actually design an optical fiber or anything like that. Okay. But there are different types of optical fiber. Which one should you use for what? Okay. With different cost and so on. So this part we'll do very sketchily, maybe in less than 2 hours, probably in 1.5 hour space. I'll just go through them quickly. And then we'll start with the actual networking part of it. Okay. So as I said, the first thing we do is, suppose we have only 2 machines connected directly by a link. How can we make them communicate reliably? That everything the sender sends, the receiver should receive it properly. Okay. So what are the issues out there? So first thing, if I so think about digital transmission, just visualize with me a little bit. So I'm sending basically 1 second. Bit pattern out there. So just try to visualize with me a little bit in your head. The sender is sending 1010. So 1 is, let's say, 5 volt pulse, 0 is a 0 volt, nothing. Okay, I send an electrical signal. How is the receiver going to know whether a 1 has a come or a 0 has a come? What do you think? Sounds a trivial question, but let me hear you anyway. Anyone? How will the receiver know? Sounds like a stupid question, right? But let's hear the answer.
Sir, like a high would correspond to a high voltage and low would correspond to a low voltage.
Simple. Okay. I'll check if the voltage is 5 volt or not. If it's 5 volt, I'll take it as a 1. If it is 0 volt, I'll take it as 0. Okay. But then just try to visualize with me. Okay. You are sending me a 10. How do I know you are going to send me? You have not sent me anything for a long time. I have to kind of, remember, this is not broadcast that is already coming to my ear. I have to kind of, something should trigger me to look for that 10. Normally what happens when you speak is your voice triggers my ear. But in electrical circuit, just think of a wire connecting 2 things. Okay, something has to be done. So it has to trigger first of all. Okay. Now there are different ways of trigger. Second thing is I need to know what is this bit duration. Okay. How will I know? I will have to sample the voltage somewhere. Where do I sample? How do I know when will you take it down? So this can be this, or if I want to send a 1 1, this will span the entire thing. So this was 1 0. Okay, I'm out of touch with this one. So this was your 1. Actually, I know what is happening. It's my problem. Anyway, I think you understand. Let's just forget about this one. So you have 1 0 and this is 1 1. Okay, so I have to sample. Okay, now if I don't sample here, instead I sample, at a larger thing, I will miss this 0. Okay, look at this problem a little later again. Okay. But basically, we need to synchronize them. By synchronization, we need to somehow we need to make the receiver know that the sender is sending data, about to send data, something, and then the receiver should be in sync with the sender to know when to sample the bits. Okay. And we'll see encoding. We don't send data directly like this 5 volt, 0 volt always. We do something else to make other things work, okay, including synchronization and so on. So synchronization is one of the big issues. Encoding is one of the big issues. Flow control deals with what if you are a slow receiver. If you speak too fast, okay, and I'm not able to process it, I can't understand. So similarly, if a sender sends too many bits too fast, and the receiver circuitry cannot process it that fast, then the receiver gets swamped. So receiver can put it in a buffer. So okay, you go there, I'll process it slowly 1 by 1. But then again, if the speed of the sender is too high, the buffer will get full. And then things will start getting dropped. So flow control deals with how to make a slow receiver not get swamped by a fast sender. And then finally, we'll see there are different kind of errors that can happen. So do error detection and control. So how do I first of all know if you sent me this, if the receiver sender sent me this 1010 and I somehow received a 11, okay? Why that can happen, we'll see. But how do I know that this was not 11 originally by the sender? Sender may have sent 11. Now I can ask the sender, did you send me 11 or 10? The sender can respond 10. But then that 10 may again get corrupted to 11, theoretically. Okay. So first of all, how do I detect an error? And the control says, if I detect an error, what do I do to ensure that eventually I get the corrected? Okay. Now, if I do all these things, I know how to send something reliably when there is one link and only two machines communicating directly on that link. But suppose you have more than two machines, but still connect link directly by a single link. So machines sharing a link. Okay. Now it's easy to see in wireless. All your smartphones, when you connect to the access point in your hostel, all of them share the same link. Okay. So something has to be done. First of all, but in a wired medium, what does it mean to connect two machines to a single? How do you connect more than two things to the same wire, first of all? Okay. And fine, if we answer that question, suppose I connect them somehow, or in a wireless question, which is easy to visualize, multiple things sharing the same link. How do they share the link with the same country? Because if 5 people talk together, it gets garbled. So there's a domain of medium access control, addressing, because if I broadcast something and I say, Abhijit, you do this, all of you hear it, but then Abhijit knows it's for Abhijit and you know it's. Okay. So the next step what we'll do is we'll set more than two machines, but sharing the medium. So we'll see we kind of slice that medium in different ways to create a channel for each pair. And then by this thing, I know how to make that pair transmit reliably. Once we know that, the basic issues, we go into building networks with any number of machines, which may or may not be connected with direct links. So this is going to be the network that you see around you every day. So we'll talk about how to organize the hardware and software. As I said, it's complex hardware and software. So you don't just start writing it in a one monolithic block. So there is layering. You've already heard about OSI, TCP/IP layers and their functions. Then we'll talk about things that you already know, LANs and Ethernet, wide area networks, which is kind of networks connecting networks. Okay, packet and circuit switching. Whenever you have a graph, you can have multiple ways of going from one source to one destination. So that's where your algorithm comes in. Okay. Then how do I find out which path to take? Okay. Because see, just think for a second. How will I, suppose you think of the internet as a graph. Okay. How will you find? And I say send from this node is my machine here in CSE. And this is the machine, this is the other node that I want to send the message to. How will I send the message? How will I find a path? What will you do? Somebody try. I give you yeah, go ahead.
Like among the machines that we have immediate contact to, if they know that they're connected to the other machine, we can send it to them and they'll forward it.
Right, but they may not be connected to the other machine, the destination. So you see, yeah, go ahead, please. Go ahead.
There's probably a global directory of some sort.
Okay, fine. So there can be a global directory. Anybody else? This is a good suggestion, okay? But this kind of saying, will kind of emphasize the design pro and con thing that we talked about. But we'll come back to it. Any other suggestion? Okay. So the first thing that you realize is that nobody knows that entire internet. So the concept of giving you the internet as a graph is infeasible. It's just too large. It's changing too much. Okay. Nodes go down all the time. Routers go down all the time. Very end of the course, I'll point out to you sites and all, which are very interesting to follow. Okay. Right now, it don't make any sense to you. Okay. So this you definitely cannot do a Dijkstra-like algorithm. Okay. But then talk about the directory. Actually, this term directory or registry is used in many different contexts in networks. But for this problem, so what is the good thing? You have a directory, you look it up and you say, I want to send to this. Please tell me what the path is. Okay, or I just need to know who is the next node, because the next node can again contact the directory and say, please tell me where the path is, because then it's kind of like the source. Okay. So, but there's an issue here also. I'll come back. So, but then somebody will have to maintain the global directory. That's also not a problem, because you will see there are many agencies at work which anyway maintains a lot of things. Okay, so it's a lot of background things that happen to make the internet work every day. But the problem is, how do you keep the directory consistent? First of all, you can understand it's going to be huge. There are billions of nodes in the internet. So will you have billions of entries? Because you may anyone may want to send to any of the other ones. And if you have billions of entries, then comes algorithms. How do you search for it efficiently? Algorithms is everywhere. There's a book called Network Algorithmics. So this lookup of the tables, okay, is a very, very interesting, fast lookup of the tables, a very interesting algorithmic problem in it. Okay. But you can understand that's going to be tedious. And the third thing is, so first of all, there are billions of entries. So how do you keep it? How do you search it? And how do you keep it consistent? Because as I said, nodes will come and go all the time. Okay. You have your laptop on now, you will have to shut down your laptop. Routers go down all the time, come up all the time. So on a global scale, maintaining this is totally going to be infeasible. But we'll see some place that we kind of do a small pseudo thing of this. So what was the problem? And second is, how will this, whoever maintains it, first of all, know about these paths? As I said, nobody is infeasible to have the entire internet graph for anybody to compute this. But this is a very good suggestion. Because see, from a design process, what were my problems? I said, the problem was basically of scale. And in a changing thing, how do I keep things consistent? These were the two root problems there. It is just billions, so I do not want to do this. And secondly, even if I do it somehow, it will keep on changing. So how do I keep it consistent? How do I learn it? How do I build it in the first place? When we do routing algorithms, we'll see basically to scale up design of anything. Okay, and this is not just networks. To scale up design of anything, you go hierarchical. You don't go flat everything. So we'll view the internet as a network of networks. And at the lowest level networks, okay, or at every step, we'll actually maintain tables. But we'll kind of aggregate information. So nobody will have to maintain too large a table. Too large is a relative term. Your higher end routers will still have hundreds of thousands of entries. But we'll take that concept, we'll say, what were the problems? It's too large. Too large, make it hierarchical. Don't think of the flat network. Think of the network as a network of networks. We'll see how we do that. So that reduces the size. Next question, now within the small size also, how do I keep it consistent? Then we'll see, we'll run local distributed algorithms to do it. But nothing can be, okay, well, let me not say that. Okay, we'll run kind of algorithms to do it. Let me put it this way, that's saying distributed algorithm. So every node will do something, it will communicate with each other and so on. See, if I wanted 10 people, okay, I can ask all of you, do you know where Ashish lives? Okay. Now, you may know and tell me, you may not know, you will say, then you know a lot of other people, you will say, do you know where Ashish lives? And somebody will know if Ashish is really there. And then that guy says, respond to the guy who asked him, the guy responds to the guy who asked him, and so on and so forth. Then it comes back to me. Now it comes back to me, I said, oh, fine, this is the path. So on a small scale, the same idea that you started with the person who answered, that I will ask others, actually works. A large scale, it does not work because then it's too much things. We look at all these issues, okay? But this is a design thing that we want to talk about, basically. Okay. So we'll do that. Then we'll do TCP and IP and some associated protocols with that because they are everywhere. And again, we look at their designs and so on. We look at configuration and naming protocols, things that make you work, that you use every day, application protocols, and other advanced topics. Okay, that we'll look at. So, what are the goals? Okay. So, first thing is understand the architecture of modern day networks. Okay, because we are doing bottom up, it will take you some time, but keep that in mind. Okay, and I will kind of link things together as I go on to the best of my abilities. The basic protocols and devices used, trade-offs involved in protocol design, scaling networks, exactly the thing that somebody has responded with. Device interconnections, and this is the other thing is we study protocols and software a lot, okay, but then I show you a switch, and you are not able to say anything about it. So you have no clue about the physical aspect of the things. So if we have a hybrid class, I intend to kind of come down with devices and their specs and so on, not including in the exams or anything, but it's good to have a feel of the things in action basically that actually make it. It's not just the software, there's a lot of hardware involved out there. Okay. And this notion of software and hardware is kind of again, what is in software, what is in hardware is relative. Okay. So if you think about a switch or a router as you have heard it, okay, which is a very costly thing. A router basically is what? It is some basic things contained in hardware, and it has an operating system which runs in the software, kind of firmware or so. When you want to make things very dedicated, general purpose, special purpose or something, make it first, we push some of the functionalities towards the hardware. So that will make it faster and we don't have to change it anyway. But then there's going to be a lot of firmware and software also loaded on it. But then if things are more general purpose or something, okay, we'll probably do it in hard software. Many people use it, reduce cost and so on. So that's one of the goals, to understand basically the modern day networks, the architecture, the protocols like TCP, IP, and associated protocols and so on. The techniques, that's the word that I miss out there. But the protocols will involve the techniques and the devices used. And at the end of the course, I would like you to explain, okay, and there will be questions in the exams, in the final exams, at least something from how some of the everyday things you use over the network works. How does your mail reach its server? A web page, you open a web page, it opens. File transfer over the net happens. Google search reaches Google. This last one will require you more things. I don't know whether we will know the thing. So you should be able to explain the protocols in play, the packet formats, the path and transformation of the packets on their way, and so on. The packet formats are another thing. You will see that there is a very specific syntax of packets, and we put overhead fields, header fields, and so on top of that. Now, one way to study them is to mug the fields. Yeah, an IP header has this field, 4 byte this, 8 byte this, 1 byte this, and so on and so forth. And this is their functionality, you can mug it. But then, and that's necessary. But then you should ask yourself, why not this field put? What happens if this field is not there? What was the purpose of this field? Fine, you said no, the textbook says you to do this. Could I have done it some other way? What were the pros and cons of that? That's how you learn systems. There's no other way to learn systems. And you always think about how can I code it? Can I build it? You always ask your questions. Okay. And this last bullet is important. There will be gaps. There will be many gaps. Okay. And you will be confused, as I said. But if you are not confused, then you are not thinking in this course. And there will be gaps, but you will see slowly, you will start getting an overall picture. You're all extremely bright boys and girls. You will see an overall picture, and then you can start filling up the gaps yourself. I will always be there to help you. Okay, some things will be off the class because some things will not be important for everybody. It will confuse you too much. But if you feel anything after, but be patient a little bit. Don't start everything in one day, first day. But let's say half the class down, you start asking yourself question, there were things that goes around and wasted. So that's all I have to say today. So in summary, I said, try thinking this, have this design-oriented thinking. Okay. Try asking yourself always the question, how can I build it? Explain the things around you. Okay. That would be the goal. Okay. And don't worry about confusion, having gaps or something. That is normal. And ask me as many questions as you want. Some of them I will not answer in class. As I said, class also has to give you some basic info, but trust me, I will answer everything. Okay. And the other thing is, in this course, because this one course will primarily cover wired networks. We'll have very little of wireless. Okay. Now, that may sound, does it sound okay to you? Let me ask you. Does it feel like we are,
No,
just
sir.
no, sir, right? Why not? Very good. That's a normal response.
Because we are going towards 5G and modern communication wireless systems.
Right. Okay, that's the normal answer. Okay, because you are using smartphones, mostly wireless devices and so on. Okay, and so you should know about wireless. You're absolutely right. Two reasons. Okay, one reason is basically it's just one course. The second reason is, remember, you are going wireless to that 5G base tower only till that base tower, base station. Everything in the back end is almost everything is wired. Okay. And still there, basically, the protocols that play, so most of the wireless changes are at the lower layers. Whereas the higher layers will, you still have, when you communicate from your smartphone and you're browsing a website from there, you're still using TCP/IP. It's the same set of protocols. Only thing, at the very low layer, when you access the medium, your physical layer thing, which we're not going to at all, and so on. Okay, those are basically changing. That's one aspect. Okay, but then there's other devices that we'll not talk about, which are very important, simply in one course. The other thing is kind of a pet thing of me in systems. See, in the front end, on the application side is all the jazz. You build great, you see different applications, you work with them all the time to do n different things and so on and so forth. Okay. And you want them to do, you want to build new applications, etc., etc. That's a common trend. You want to do machine learning, this, that, etc., etc., etc. But then there has to be systems, which includes both servers, operating systems, networks, okay, that are absolutely necessary when these applications are going to run. So you, as a CS student, okay, to me, cannot say that I will take that backbone as granted and I will build applications on top. So somebody has to build that backbone. Okay. And I say this, I digress a little bit, but I say this because it's, I have very you are just in third year, so you should care. I have seen people graduating with a dual degree, 4-year, 5-year degrees. Okay. And their last semester, teaching them distributed systems. Okay. I have seen they have no idea, for example, what does a server look like? Okay. I'm not saying how does it work, what are the intricacies and so on and so forth. 50% of the students say servers look like just like the PC. And they do, there are tower servers. But then there are different types of servers. Just in physical form factor I'm talking about, not internal working or anything. So when I take them to a CSE lab and we show them the servers, wow, this is the server, this is the rack. Now that is not acceptable to me. Okay. And trust me, systems jobs, the job space is huge. It's extremely difficult to find very good systems people. You ask your seniors, anybody. Okay. Applications, obviously, there's a lot more applications, so there's a lot more jobs in application. But systems jobs are there a lot, and they're very hard, very high paying because it's hard for they're in demand. So in answer to your question, okay. Ideally, that's one thing that we will discuss the last lecture of the class. That if once you have done, it's just a one first level core course. After you have done this, what all can you do? Where can networks go? Okay. See, for example, you talk about these Google things. You have heard about the term data center. They're everywhere. Your clouds, your Google Cloud, everything is in data centers. Even though wireless is being used in data center, the primary part of data inside what happens in data center, the networking, is completely wired. And if I have time, I doubt whether I will, but then at the end of the course, you can talk offline with me. Designing the network in data center, okay, has different kind of criteria than designing a normal network like in an institution like IIT or something, or even a larger institution. So most of we will not do wireless, okay, except for that little bit of sharing medium and so on, okay, because first of all, it is one course, you cannot cover everything in one course. And secondly, there's a huge chunk of the network, the entire backbone, which is primarily wired. So you need to learn them, you need to know how to design them. And this is an extremely fascinating field to work on. Either you're doing research or you're going into a job, basically. But yeah, of course, if you could have done wired and wireless, everything could have been great. But then you would not have learned anything. Basically. You would have just skimmed over everything. You just learned some terminologies. So with that, I end. Okay. This class has been confusing enough, I'm sure. Okay. But that's okay. So from next day, we start, as I said, we'll start with transmission basics. But then we'll have very few, kind of do it very sketchily, and then we'll actually go into the other things. First of all, do you have any questions? Don't leave yet. Do you have any questions? No? Okay, so I'll just start it. So we'll do that. And
Excuse me, sir.
yes.
So is there a course webpage? Like, what is the link?
Yes, it's in the first slide. I'll share the cscrdkgpc.in/ see have the recording on, right? Oh, I don't know whether the recording was on at that time. So cscrdkgpc.in/tilde-gupta/networks. Networks. Okay. So it's hardly anything there right now. I'll keep on putting materials as we go. And all these books that we have said, okay, I cannot, okay, let me turn off the recording.